Hi everyone, my name is Michael, and this is the first part in 3 of a podcast series with Professor Michael Meyer from the University of Michigan. The subsequent episodes will be released next Friday and the Friday after that. When the 4 of us started a podcast last fall, Michael Meyer was one of the first professors that came into mind to bring onto the podcast. Tommy, Sam, and I all had him as professor last year, and as you will see in this episode, he is very, very knowledgeable about everything astronomy, and his passion on the subject is very contagious. Hope you enjoy. So thank you for joining us today, Professor Meyer. How are you doing?
I'm doing great. Thanks for inviting me.
Yep. And so I think one of the most interesting things is that you, in terms of being a Michigander, you're quite recent in Michigan. You've only been at the university for the past 3 or 4 years now, but before then you've had a lot of experience elsewhere in the United States, as well as around the world, especially in Europe. So I was wondering if you could kind of bring us on that journey, starting from when you were a kid, what first got you interested in astronomy and research, and when everything kind of clicked as to seeing science as a viable path for your career.
Well, I think what got me hooked or ignited a spark was the PBS series Cosmos in the late 70s. I guess for me, it would have been early 80s. I don't remember exactly when the first airing of Cosmos was, but it was in popular culture and people were talking about it. And I saw it on our local PBS station and I was really obsessed with Cosmos. And so I subscribed to Astronomy magazine and I really thought space and astronomy and science was cool. I remember at the time, there was no internet. And so we had a World Book Encyclopedia, which was kind of our version of a hyperlinked text. And I remember I'd stay up late at night and I'd have like dozens of different copies. It went by letter. It started with A, B, C, and different volumes were the different letters of the alphabet. And so you'd read an article about space and then it would say at the bottom, see also, and then it would like drive you to new topics. And so I'd be flipping through on astronomy and then planets and this and that. And that was kind of like hyperlinking. So I remembered that experience of jumping around topic using the World Book Encyclopedia. Anyway, I then just always thought it would be so cool to be a scientist. And I have to say, I didn't read Astronomy magazine every month, even though I subscribed to it and I couldn't understand most of it. So then they would stack up and then I stopped getting it because this is a waste of money. So I had kind of a hard time engaging with local amateur groups that I thought were kind of sophisticated or sort of over my head. And it was sort of not fun sometimes. Or things got too technical. I had a hard time keeping the passion going. But when I always thought I wanted to go to university to study astronomy. And my family is not all of them, went to college, and my dad ended up going into the Army and worked nights and went to school during the day with 3 small children, blah, blah, blah. So it was a very different experience for me to think about going to college and studying something just for the sake of learning about it, as opposed to it being an absolute means to an end. My dad did get a college degree, but he himself was certainly a non-traditional student, and none of my grandparents went to high school. So I kind of don't come from a super well-educated family. So I didn't really understand where to go and think about, how would you study astronomy? That was so weird in my community. So I called up the local planetarium in St. Louis, Missouri. And the person is like, yeah, we're the planetarium. This is not the right place. But he got it. He understood what I was coming from as a junior in high school. And he directed me to a local university professor who was sort of, at the time, one of the only working astronomers in the state of Missouri. This would have been 83 or 84, I guess. And he gave me great advice. He said, if you really, 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 really know already that you want to do astronomy, you should go to some place that does astronomy. But, and he said I should look at the University of Arizona. And I had never really thought about something like that. But he also gave me even better advice. He said, but my recommendation is to study physics. as an undergrad, and you can do that almost anywhere.
Right.
And so that's what I kind of ended up doing. I went to college at Washington University in St. Louis, Missouri, and I was a physics major. And as I started learning a little bit more about science and getting more technical in my knowledge, I started thinking, oh, well, doing laboratory experiments and physics is really detailed, and you can get real answers about atoms and molecules, and that's really precision science. And astronomy is so ridiculous. You can only learn anything to like a factor of 10. And is that even science if you don't know the answer to better than a factor of 10? So I kind of got disillusioned with astronomy as a physics major. And then I had a good fortune to work. In fact, I can't even remember how I stumbled in to talk to this guy, but there was a person in the Earth and Planetary Science department, neighboring department, that needed a lab assistant. And so I started working with him one summer, and he was basically doing planetary astronomy, like looking at planets and imaging with CCD cameras that he built in his lab at telescopes in Hawaii. And I was like, wow, this is cool. So I really got the bug again working with him, and particularly got exposed to instrumentation and data taking and stuff like that. And that really kind of solidified my experience. I tried to apply to graduate schools. I also should mention that I had to interrupt my studies at WashU to take a leave of absence for 3 semesters for financial reasons. So I did 3 semesters at the University of Missouri, Columbia. And I think between it was the second semester of my sophomore year and my whole junior year. I think you could imagine that's somewhat disruptive for a curriculum. Right. So it was not a good idea to do that. And in retrospect, I might have fought harder to try to not do that, because I don't think that was super wise. Like if I had gone 2 years to some place and then transferred, that would have been much better than like starting one place, going for a year and a half elsewhere, and then coming back and finishing as a senior. That was not a good idea, and I would not recommend that. But I also wasn't an A+ student just in general. I kind of had some holes in my background as a high school student, and didn't really, and then I was not challenged that much in high school. And so I didn't really know how to study or have like a big goal that I needed to overcome and figure out how to be disciplined and do that. In my family, it was much more important to work outside the home. And so from 14 on, I always had a part-time job, mostly working in restaurants, first as a busboy and later as a waiter. And while it was great to have a lot of spending money, I didn't really apply myself in the right ways as a young person. That happened in college too. I worked a lot in restaurants. So anyway, I didn't get into graduate school when I was a senior. And so I had to kind of regroup there. And I decided to go to a local commuter university and offer myself as a graduate student there. I got a job as a teaching assistant. And I spent 2 more years going through their terminal master's program. So I took, 2 more years of courses. I then, in those days, of course, the physics GRE was a key part of your applications to graduate school. This was in 1989, 1991. And I really studied hard for the GRE, for that second ramp at grad school. I think I spent 6 months, and I did every single homework problem up in Halliday and Resnick, just all 30 chapters over and over again. And I basically doubled my score on the physics GRE. And of course, I had 2 more years of courses, and I got more exposure to research. And then there was an astronomer there. In fact, that one I had called as a high school student was still working there. And there was another astronomer then at that time. So I got into some research in infrared astronomy and star formation. And then coupling that with the laboratory work I had done kind of made a nice package for me. And it gave me a direction about where I wanted to go with this astronomy stuff. So the second time in 1991, when I applied to grad schools, I got into several different places, was able to go visit them and tour around, and it felt really good to be being recruited as opposed to being so totally shut down the 2 years earlier. Right. And in the end, I decided to go to the University of Massachusetts in Amherst, which had a very strong star and planet formation program and infrared instrumentation, which is what I wanted to do. And then after that, I had a little trouble getting on my first postdoc. I had a wonderful experience at Amherst, and I just learned a ton and really got confidence and got exposed to how to do research within a group and learn as part of a research community. And part of my research style I learned there, which was to kind of master the background information, the literature, and to be part of a community and to tell stories, to come up with hypotheses that kind of linked together the work that had been done in the past and try to spin that forward into new ways of thinking about the problem. And that research community plus the storytelling really inspired me to try to do my best in research. And that's sort of where I started to see more success. I barely got a job coming out of grad school, though. I didn't write enough research papers as a graduate student. And I actually got a job only because I had called someone in sending my CV to someone that I had met at a conference in Germany the year before, which I only went to. My research group couldn't afford to send me, so I paid for myself to go to this conference in Germany. And I met this person, and we hit it off, and they liked my research. And then he did not advertise a job the year I needed one, but I just sent him my CV and my application anyway, and he ended up hiring me. And that was the only job I got that year in 1995. And so I spent 2 years there. Then I was able to come back on a Hubble Fellowship, and I took it to the University of Arizona. So I finally heeded that advice I had gotten in high school at the Stewart Observatory. And I worked there for a couple of years and then was invited to join the faculty. Spent 8 or 9 years as an assistant and then associate professor there. And then in 2009, I moved to the Swiss Federal Institute of Science and Technology in Zurich, Switzerland. I had an opportunity to start a new research program there and a new group, and to join what was already an excellent exoplanet research community in Switzerland. And then partly for family reasons and other reasons, we decided we wanted to come back to the US. Both my wife and I have aging parents in the Midwest. I'm from St. Louis, and in the out mid Missouri area, and my wife is from Chicago. And so we wanted to be closer to them, and University of Michigan was able to make an opportunity for us at the right time, and we're very, very grateful and have really enjoyed being here the last 3.5 years.
Professor Meyer, could we touch back on this problem, I think, in high school, that astronomy is one of the most captivating subjects, but a lot of people then go on to study physics or physics or just get turned off by science because they can't get involved, and it's quite hard to get involved in astronomy. But the cool thing is that now with the internet and all of these resources, people can get stuck in easier than they could before. Could you sort of describe for our audience a little bit some things that people could be doing in high school, or some interesting things that are out there that are perhaps not so well known, but that exist to get interested and keep the spark of astronomy alive?
Wow, citizen science is a new amazing frontier. There was even a story, I guess in January or February, of someone who had just joined a research outfit for NASA, and within a few days, as an intern, as an unpaid intern, and discovered an exoplanet from the test mission. Within like 2 days of starting on the job, working with folks at MIT. So citizen science is an amazing thing. I think you may have talked about this in your group before, that the Zooniverse is a wonderful gateway to many kinds of citizen science opportunities. And currently, there are opportunities for citizen scientists and high school students to go through test light curves by eye and look for unusual things. And it's not that we will mine the database visually with humans, for the next 5 years to find exoplanets. Right. TESS is a transiting exoplanet science mission that was launched by NASA a year and a half ago and is doing wonderful work. But by inspecting and reporting unusual things, we are training neural networks and machine learning algorithms. So humans are still the best way to teach robots what to do. And there's just an absolute huge amount of work for people to do to really help in doing real science. I should also say that I'm part of the TESS Followup network. We tend to do things like look for blended companions with adaptive optics at our Magellan telescopes, to which Michigan has unique access, or not unique, but preferred access. But many people who are amateur astronomers use small telescopes with CCD photometers and do photometry from their backyard. that is really vital to the whole TESS mission. So, and that's real data taking where you upload the files and people do photometry or astronomers at home do them themselves. And it's really a very, very important part of the mission. So there's something called the TESS Follow-Up Network, TFOP, and you can find links to that through the MIT website, the MIT Mission Control for TESS, TESS. So there's amazing ways. I should also say it's not uncommon for us here at Michigan to get requests for internships from just people who may even go to college elsewhere than Ann Arbor, but who live in the Southwest Michigan area in the summer, and then they volunteer for free to do research. And people, you know, I would have never ever thought of doing that in the mid 1980s, but it's quite common now. And a lot of people even come to college with some kind of research exposure of one sort or another. So I think there are fabulous ways to get involved locally in whatever kind of community one is in. And of course, the internet has made all of this possible.
And I know you do offer the unique perspective because you mentioned that there's a lot of local and national research that you were involved in and that people can get involved in, but you also had a lot of opportunities to do international research. So we're kind of wondering if you can explain and elaborate how research in the US compares and differs to research, say, in Germany or in Europe, and how different projects could be connected, or how those processes go.
Yeah, wow, that is a whole hour-long topic on its own. But let me say that it was very valuable for me as a postdoc to go and work for the Max Planck Institute for Astronomy, which is part of the Max Planck Society in Germany, and see that different way of doing research. In Germany then, and it's somewhat persisted now, there is a longer-term commitment to most of the funding lines that are available. So one of the things that is a hallmark of Central European science funding is consistency. There is a very steady growth with inflation, and budgets are flat but rock solid. You would never experience a 20 or 30% budget cut due to an economic crisis. And I even lived through this in Switzerland during the Great Recession of the late zeros and into the early teens. We didn't even notice that there had been a financial crisis in terms of our research funding until about 5 years into it. Then we got a little bitty dip and then things came back up. In the US, for good and bad reasons, there is much more of a boom and bust cycle. So if you go back and look at the history of the National Science Foundation, even in the last 15, 20 years, you'll see campaigns or emphases that we want to double the biological science budget in the next 5 years or something like that. And so you'll see these huge ramp ups and then things will flatten. And then in crises, you'll see things really cut. A lot of the discretionary spending in the federal budget can be very volatile, due in part to economic, very reactive to the economic circumstances, which to some extent is reasonable, and also different priorities of different administrations. It's very, very difficult to plan out 10 and 20-year program budgets when you know that every 4 or 8 years you're going to be facing a very different set of priorities from different administrations. And you can see that perhaps all through your own lifetime. During President Bush in the zeros, there was talk of going back to the moon and Mars. And so things happened, and then they didn't happen, and then they happen again. So it's been a little bit this lurching. That can sound bad, but it's also true that kind of extraordinary increases can happen in remarkable times. And you can just say, yeah, we're going to do this. And 5 years later, it actually happens. So it's much harder in Europe to get like a gigantic project just launched off of the ground that would cost, $1 billion in the next decade. That just is not going to happen unless it's part of a 30-year long plan. And to some extent, that's true in the US too. You can't just plop $10 billion down on something. But the US is more volatile in the plus and the minus direction. So it's easier to do more steady, longer term things in Europe. I should also just say, though, that the whole university structure and the whole research institute structure is fundamentally different. The US, again, for good and bad reasons, can benefit from philanthropy. So people who have done very well in the private sector can become major sources of research funding. and this is something that really surprised me as I came back to the US in 2016, I've really been trying to tap into some of these philanthropic foundations to fund a lot of my research. And in Europe, that would be unheard of. You really wouldn't. The government is funding research enterprise, and you would not expect wealthy people. That is definitely something that the state is expected to do. I guess the other major difference is, of course, it is a nation-state model, and there are continental entities, but these are member states that band together. For example, the European Space Agency,
Right.
which for good and bad reasons just operates very, very differently from NASA. And also each national science funding agency just operates on its own. And the federated European things are really only ESA and the European Southern Observatory, neither one of which is tied to a particular political union. So they are not part of the European Common Market. They are not part of the European Union. They are their own by multinational legal entities that are not necessarily connected to politics or policy of different governments. So it creates pluses and minuses there too.
I think one interesting thing you mentioned, starting even in high school and early college, undergraduate years, is how your research goals and interests have kind of stayed the same over the course of your career, in terms of starting out thinking about instrumentation, thinking about stars, planet formation. And I'm curious to know how over the years your research has evolved and changed, and how maybe your outlook as to what you're interested has changed.
Yeah, so I think what I tell my mentees, people that I work with as undergrads and grad students and postdocs and such in my research group, is that the more you know about something, the more you're interested in it you tend to be. And so when I was first starting out, I'm not even sure how. I think I had to do a term paper on it. I got really interested in ultra high energy gamma rays. So these are very high energy radiation particles. They hit the atmosphere. They create secondary cascades of charged particles, which themselves create tertiary and fourth order cascades. And you see the showers come down, and then you try to pinpoint the source of the TeV gamma rays celestially, but you can only do so with, in the 80s, you could do that with an accuracy of several degrees. Now we've gotten a lot better, but I just thought that was super cool, like the highest energy radiation in the universe. And then I got interested in the lab I was working in spectral polarimetry. So spectral information, but also encoding the polarization vector of the light, and instrumentation that would allow you to do that. And then I started to try to merge the two, and I was interested in BL Lacerte objects, BL LAC jets, and I was going to try to study proton synchrotron emission in the infrared with the spectral polarimetry. And then I got exposed to infrared astronomy and star formation. So it just kind of started building on its own. I think the thing that I hit on that stuck was a bit combining the instrumentation with the infrared astronomy. And then the star and planet formation is a very obvious application of the convergence of those two interests in infrared and instrumentation. And then because of that, I chose to go to one of the leading groups at the time in star and planet formation at the University of Massachusetts in Amherst, the 5-college astronomy department. And there were, gosh, I think 6, maybe 7 different research groups, all in that area. And then it's just popping. You know, I learned as much from the graduate students I went to school with as the half a dozen postdocs who were running around studying similar things, as the 4 or 5 professors who really ran the group. And then there was another research group in the interstellar medium, and that was where Professor Bergen was a graduate student. We were graduate students together at UMass. And so it was just a very rich environment and an exciting time in that field. And so when things are going well and they're interesting, and you see a lot of energy and excitement around you, and you're making progress and learning new things, you get more passionate about that topic, and you learn more about it, and you get more steeped into it. I guess for me, the big pivot, if you will, was when exoplanets were discovered. So the month I defended my thesis, the first detection of a gas giant planet around a normal star was made at a conference I was supposed to and give my thesis talk at, but I didn't go. I canceled the trip. because I was just rushing around too much trying to finish. And at that meeting, they announced the discovery of the very first bona fide direct detection of a brown dwarf and an exoplanet in October of 1995. And then a paper came out in Nature in November, late November, early December, and it just exploded the field. I had been in a group studying the structure and evolution of circumstellar disks around young stars for many years by that point. But we always talked about planet formation, but we never really kind of jumped to say that we were looking for other solar systems because we thought that would be too speculative or too flashy when you didn't have the data to back it up. But once exoplanets were discovered, then the whole field exploded. And those of us who were already kind of studying planet formation moved closer and closer to studying exoplanets. And a lot of other people jumped into the exoplanet game just in the observational side of detection and then later characterization. And it just led to a real renaissance in the field. And I guess now I describe myself more as someone who's studying the discovery and characterization of exoplanets than as someone who studies star and planet formation. But of course, I bring all that with me. And so I still occasionally do star formation related projects, and some students are interested in working on those kinds of projects. But I guess certainly in the last 15, 20 years, I have moved steadily and closer to exoplanets for sure. Because
So-
they're more, because of opportunity. You know, it's just,
Right.
wow, I can contribute here, and I move there. And that was a very natural evolution for me.
Mhm.
So you briefly described that that your role is in globally looking for and classifying and characterizing exoplanets. But could you go a little bit further into what it is that you're doing? What are the hypotheses that you're testing? Because I imagine that even before exoplanets were formally discovered, there was presumably an inkling that they would be out there, given that our solar system doesn't seem to be that unique, I would think. And so, but however, it must have seemed premature back then to just speculate about exoplanets and their science. But now that that is becoming a real, now that that's a mainstream scientific area, what are the sort of hypotheses that are being tested by scientists in that field?
So I'm glad you asked the question in that way, because that is the way I try to approach it. I still think of myself as an experimental physicist at heart.
Mhm.
And I still remember, I ask my kids if they get this in school. We were taught a version of the scientific method every year in grade school, as far back as I can remember. And science doesn't really unfold that way, but there is a certain methodology of thinking about an hypothesis that can be ruled out. And this is something that I really try to emphasize to my students and other mentees, that if you're doing science, and I'm using that with a capital S, you would like a hypothesis whereby if you go looking for something and you don't find it, you can rule out a theory or some hypothesis on the basis of not finding what you're looking for. And that leads to good experimental design. And that means you can't lose. If I'm awarded 10 nights on an 8-meter telescope, I could find a planet and, wow, that's cool. And I'll publish that as a high profile detection. But if I don't see anything, the upper limit on their occurrence has got to be meaningful. So I've often been accused of kind of, making lemonade out of lemons. If I did this study or that study and I never find anything, I'm always spinning these little stories about how magnificent it was I didn't find anything. When of course, deep down inside, I was like, I totally want to see 10 planets, but I found zero. So to answer your question, what I am trying to do is to test quantitatively and confront theories of planet formation that should be predictive. They should have specific predictions that they can make, and then I look for what they predict, and then if I don't see it, I rule out that theory. And in particular, the way we talk about that is exoplanet demographics. I would like to know how common planets are as a function of the planet mass, maybe as a function of the planet radius, maybe as a function of the orbital distance from the planet to the star. And these distribution functions we call demographics. How common is a 1 Jupiter mass planet at 5 AU, a 1 Jupiter mass planet at 0.2 AU, a 1 Jupiter mass planet at 30 AU around sun-like stars. And then that now I've kind of designed an experiment. That means I need different techniques to characterize the frequency of planets between, and I said one Jupiter mass, but now let me be quite clear. I need to measure it over a range because I can't just have them be 1.000. That's too specific. So I say, I need to measure the frequency of planets between 0.3 and 3 Jupiter masses over a range from 0 to 0.5 AU, from 0.5 to 6, from 6 to 20, and from 20 to 1,000. So now I've separated 4 ranges of orbital distance, and now I've got a planet mass range, and each one of those ranges might require a different technique to find the planets. And I want to go as sensitive as I can and be as successful as I can. But more importantly, I need to know the limits of each survey that I would design, what sample size I need. If I'm going to look at 3 stars and I find nothing, well, that's kind of maybe not a very robust result. If I look at 130 stars and find nothing, you can think of Poisson statistics on a probability of success going as the square root of the number of experiments you try. So 130 is getting up there. So that's a good sample. And therefore, we try to learn how common planets of a different type are. And then if I do that whole thing, I repeat that experiment for stars that are much higher mass than the sun, what I would call intermediate mass stars, say 1.5 times the mass of the sun up to say 3 times the mass of the sun. And then I repeat that experiment again for low mass stars. And there, I'm kind of doing a planet formation experiment. And the big knob that I'm twisting is stellar mass, which I think gives us a big handle on planet formation around stars of different type. And ultimately, I would like to be able to predict how common planets of a given size and orbital separation are around all types of stars, even ones that I can't observe in galaxies that are 1 million light years away, going back maybe to the early universe. And yes, eventually, if we want to use these kinds of observational programs to constrain the frequency of rocky planets that might be in the liquid water zone of their host stars. And ultimately, we would like to place constraints on the probability of biochemical origin of life in the universe.